everybody, I'm back, this time with electrical engineering. Fun stuff. Anyways, this is actually pretty simple. This is going to be our third quiz. It's on, well, steady states and like the interim spaces. Like, what is it like when it's steady? What is it like when it's just changed? Basically, that's the idea. Anyways, in this particular case, we have this circuit you can see here. And for part A, these are the particular givens. They may be different later on. I haven't looked ahead yet. But what he wants us to find out is this I the current that's going through the conductor at this particular time, which is right before the switch closes. So it also wants you to draw the equivalence circuit. Let's go ahead and do the equivalent circuit and then use that image to find our IL of 0. Okay, so we've got our voltage source. There's our voltage source. Because that switch is open, it's as though that resistor were not even there. Okay. Alright, now it's in steady state beforehand, before the switch is closed, which means that this L acts as though it were just wire. Okay, so L is insignificant. We can pretend that's a wire there. Alright? But the I of L is still measured at the same place. Okay? So, the I of L is conveniently, this is a very simple circuit, I is the same everywhere. You know, we could throw capacitors in here, we could throw whatever, but it's all in series. So, the current is the same everywhere. The current across this inductor is just the same as the current across the resistor. Alright? So, we can pretend that this is wire. So our actual equivalent circuit looks more like this. Alright, we don't have to worry about L. Those are R2. Alright, so we've got a voltage here, which is 12 volts, that's given. And then we've got R2, well, R2, D2, but anyways, never mind. We got R2 is 1 ohm. Yeah, I imagine he has a lot more ohms than that because, you know, kind of a complicated little droid there. I don't think his resistance is that small. Anyways, yeah, sidetrack. So the function for voltage across a, well, let's do this first. Kirchhoff's voltage law. Here's one node. Here's another node. What am I doing? Voltage law. Loop. Okay, here's my loop. Tiny little loop. Okay? So we can say that we know that the current is going to be going something like this, so we want to say that this is positive and this is negative. So V, I'm going to call it V2 because it's for R2, for the resistor. Oh, what am I doing? That's not R2, that's R1. I got distracted by the R2 pun and then totally did not realize that I'm actually looking at R1. Anyways, so the voltage across the first resistor minus Vs, because you're going backwards here, you're going from the negative to the positive, so it's minus Vs, equals 0. That's Kirchhoff's voltage law. So V1 equals Vs, piece of cake, 12 volts equals V1 is IR, because we have a resistor, so it's I times R, which is 1 ohm. Therefore, we can conclude that I is 12 amps. Alright? Because there are really only two nodes, here's one, here's the other, there's really no other place for the current to go, so the current is the same everywhere in this circuit. So we know that the I of L is equal to the I across the R, I'll call that I1. So this also equals IL. And that's your answer. This is your equivalent circuit. Things you need to know for this is KVL and voltage of a resistor. And that's pretty much it.